In this session, we're going to look at molecules that have multiple chiral centers, or at least two or more chiral centers, which gives us the opportunity to have diastereomers and also to have meso compounds. So here's an example, 3,4-dibromohexane, which has several stereoisomers. See if you can find the chiral centers and calculate the number of stereoisomers that are theoretically possible. Pause the video here if you want a few minutes to try that. So in this molecule we have two chiral centers, the number 3 and 4 carbons, each of which have a hydrogen, a bromine, and an ethyl group. And since we have two chiral centers, we have 2 squared, or 4 theoretically possible stereoisomers. And so let's think about a couple of those. And this is actually an example where it might be useful to use Fischer projections. So I'm going to draw those first for our discussion, and then we'll go and look at the wedge dash pictures as well. With the Fischer projections, we could have our CH2, CH3 groups on top, and then our bromines we could either have both on the left. We could have top on the left, bottom on the right. We could have the other way around, top one on the right, bottom one on the left. And we could also conceivably have both bromines on the right. And if we look at those, there are a couple of things that we want to notice. First of all, that the two on the middle, or in the middle, are actually mirror images of each other. And they're mirror images that you could not superimpose. So there's no way you can take the one on the left and put it on the right and have everything match. That makes them enantiomers. Notice also that the first two structures are stereoisomers, right? They're both 3,4-dibromo, but they're not mirror images. And stereoisomers that are not mirror images are called diastereomers. Let's practice saying those words. So repeat after me. Enantiomer. 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 Diastereomer. 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 Each compound, by the way, will have only one enantiomer. It can have multiple diastereomers. If it's chiral, it always has an enantiomer. It may or may not have a diastereomer. The last thing that I'd like you to notice is that the structure on the two structures on the ends, this one and this one, are actually identical. If you take the structure on the right and rotate it around 180 degrees, the two bromines are going to be on the left, and it will exactly overlap the first structure. And since it is the same as the first structure, And we really only have 3 stereoisomers where 4 were theoretically possible. Another thing to notice is that those two, because they are mirror images, but they are also identical, that neither one has a mirror image that's different. The mirror image is the same. That means it's not chiral. So that structure, represented by the first picture and the last picture, is achiral, and yet it has 2 chiral centers, which means that it's meso. And notice that it also, because it's, one of the things that makes it meso is the fact that it has an internal mirror plane. Now we're going to take a look at the models of these as well. And the first one, the meso compound, is shown here. And it should be pretty clear to see the internal mirror plane in this compound when it's in this configuration, because the both 2 sides are essentially mirroring each other, right? Where there's a bromine on one, there's a bromine on the other. Now note that if we were to turn this around to make it a staggered conformation with the longest continual chain zigzagged, it would be much more difficult to see that. That would give us this configuration. And we could do a wedge dash picture of that. We'd have our zigzag chain. We'd have the bromine on the left wedged up, top of the page with a wedge. The second bromine on the right would be dashed and down. Now if we take the middle molecule, where we have the bromine on the left on top, on the top cross, and then the bromine on the right on the bottom cross, right, again it's an eclipsed conformation here because it's a Fischer. We could do the same thing. We could do a rotation around and make a nice wedge dash zigzag thing. Both of our, in this wedge dash, both of them would be wedged, right, because they're both pointed out at us. And notice that if we took those 2 structures and tried to superimpose them, that part of the molecule matches, right? So the carbon over here has the same absolute configuration. The carbon over here is a mismatch, and so the absolute configurations would be the opposite. So when you have a partial match and a partial mismatch, then you've got a diastereomer, because they're different, but they're also not mirror images. And if we try to turn them around so that they face each other, right, we can see on the top chiral center the 2 bromines pointed away from each other. That mirrors, but here it doesn't mirror, because on the one side you've got the hydrogen and the bromine, the top side so to speak, the hydrogen and the bromine are looking at each other, whereas on the bottom it's bromine hydrogen, so you don't have mirroring there. And if we take a quick look at the enantiomer of that we just saw, right, it's a little easier to see how these 2 mirror each other, because on the top one we've got wedges on both, but they're pointed, the top one is pointed away from the bottom one. In here we'd have wedges for both of them, but they're pointed towards each other, so they more clearly mirror each other. And there's just simply no way we can turn them around to try to get them to superimpose, because every time we do, there's a mismatch at both carbons. And if there's a mismatch at both carbons, that's going to tell us that we have mirror images.